Hello, AP Chemistry students. This is Mrs. Ottman. We are on video number 10, Bonding Part 2. Here are our objectives for this video. Pause here. Right, so we're not going to be doing any calculations with Coulomb's law. Those of you who have taken physics in the past, you may actually recognize that this is not the full version of Coulomb's law. I removed the K value from it, 10 to the ninth. You don't need it because we're not going to be doing any sort of calculations with it. What we care about is the fact that the force between two charged particles is directly related to the charge of each of the particles and indirectly related to the distance between them. So we represent charges with Q1 and Q2. It doesn't matter which one you call 1 and which one you call 2. And then R, it's called R because radius, it's the distance between charges. Charge is measured in coulombs. We'll talk more about that in chapter 18. And the distance is going to be measured in meters, just like how wavelength is measured in meters. Same idea here. Pause here. All right, so we're going to be applying Coulomb's law to lattice energies. The lattice energy is the energy that is released when a crystal lattice is formed from its component ions. So we're talking about ionic solids here. So this is not proper bonding, but it still has a similar sort of idea to it. So remember when we talked about bonding, we knew that every time you formed bonds, it was exothermic. A similar thing happens here. So when you're forming these ionic, they're not exactly bonds, but bonds for lack of a better term, you're going to release energy. And then following Coulomb's law, if you have highly charged ions like +2 or +3, or if you have shorter bond distances, then you're going to have a higher lattice energy. You're also going to sometimes hear this called lattice enthalpy. You can use them more or less interchangeably, even though energy and enthalpy are not exactly the same thing. But for experimental purposes, they can be used more or less interchangeably. Pause here. So lattice energy enthalpy also relates to dissolving substances. So whenever you're going to dissolve a substance in water, there's going to be three separate steps to it. The first is that the solute, the thing that's getting dissolved, must break into smaller pieces. That's endothermic. You're breaking these forces. The second is the solvent must create some space, like actual physical space for the solute to go into. That is also endothermic. Whereas the third step, when the solute and the solvent combine, meaning you're taking charged particles and you're bringing them together, that is going to be very, very exothermic. And so some dissolving is endothermic, some is exothermic. It really depends on the relative endo or exothermic properties of steps 1 and 2 versus step 3. Pause here. All right, so let's discuss this. So both solids have the same ratio of charges. So we've got a +2 charge and 2 -1 charges. But Mg has a smaller atomic radius than Sr, so there is a shorter distance between the charges, and thus MgOH2 has a higher lattice energy than SrOH2. So essentially, if you if there's a difference in charge, you'll talk about that. If there's a difference in distance, you'll talk about that. It's always going to be one or the other. Pause here. All right, so now we're sort of switching gears and talking about bonding again. This is sort of related to what we did in chapter 6. So sometimes bond enthalpies of specific bonds are going to be known, and then we can actually use it to determine the overall reaction enthalpy. So this is something that is in the same vein as using Hess's law or enthalpies of formation. Unlike Hess's law and enthalpies of formation, instead of doing products minus reactants, we do reactants minus products. The reason why is because that gives us the correct sign. We need to add energy to break bonds, hence reactants being positive, and we need to release energy to form bonds, hence products being negative. So if enthalpy is positive, that means you added more energy than you got back. Not saying you're violating the law of conservation of energy, it went somewhere else. But if enthalpy is negative, then more energy is released that was used to break the bonds. Pause here. All right, So let's take a look at this. We are going to be doing reactants minus products here. You could ignore this delta S thing. That will have more meaning later. So the N2 bond is 946 kilojoules per mole. And then I've got 3 FF bonds. I don't know what they are. I'm going to call them X minus. If you actually draw out the resonance structure, the Lewis dot structure for NF3, you'll see that there are 3 NF bonds within it, and there's 2 of them. So I do minus 6 times 272 kilojoules per mole. And I set that equal to the enthalpy of reaction, negative 264. And then from here, you just have to solve. So I got positive 141 kilojoules per mole, and that would make sense there because I am looking for the FF bond, which should be pretty similar to the NF. I was looking for the FF bond, which will end up being pretty similar to the NF bond because both elements are pretty similar in electronegativity. And then here are the additional practice problems for today's video. Thank you so much for watching and have a great night.